This is a tale of love, friendship, and of course, Bayesian network theory. Once upon a time, upon a hill stood a factory where all the workers lived happily in harmony with each other, when suddenly the alarm sounds. All the engineers and technicians looked up with question marks above their heads, wondering what's going on. The alarm of the factory is designed to sound off in only two situations, one being a leakage in the cooling pipe, the other being a high temperature in the reactor, which is dependent on the leakage of the cooling pipe.
From previous data collection, we know that the probability of the cooling pipe to leak is 0.3, and T here indicates that the condition is true, or it does occur, and F is false, or when it does not occur. This table shows probability of the reactor reaching a high temperature due to the leakage of the cooling pipe. As the high temperature of the reactor only occurs when there is a leakage in the cooling pipe, the probability of high temperature is 0 when there is no leakage in the cooling pipe. And this table here shows the probability of the alarm sounding under conditions in the left column. Now, how would you know which condition actually caused the alarm to sound? I know! We can just check if there's a hole in the cooling pipe, right, Brain?
No, Pinky. As you can see, this alarm, as said before, only sounds under two conditions.
Yeah, but still, can we just look for a hole somewhere along the pipe?
Oh, yes. Anyways, here's the probability of a cooling pipe leakage given that the alarm sounds. We can then expand the equation.
On the numerator, both the scenarios with high and low reactor temperatures were calculated, knowing that the cooling pipe leakage does occur.
And to combine the probabilities of all the conditions causing the alarm to sound, we sum all probabilities that could lead to the alarm sounding in the denominator.
And, using the values from table shown before, we obtain a value of 1. Why is that so, Brain?
It's simple. The alarm always sounds due to a cooling pipe leakage, regardless of the reactor temperature.
Ooh.
Now, we will determine the probability of the alarm being triggered because of a high temperature alone.
Isn't this equation the same as before?
No. In this case, high temperature has been set to always be true, but both cases of whether cooling pipe leakage occurs or not have to be calculated. Then we go through the same big steps.
And here's our answer.
It looks like there's a 92.7% chance that the alarm is due to a high temperature in the reactor.
Does it mean that there's a hole in the pipe then, Brain? 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 Oh well, guess I'll have to do the ending alone then. Na 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 na. The end. Oh yeah, and they live happily ever after.